Okay, this is going to be the rest of Chapter 8. This is going to be covering sections 6 through 8, except the ideal gas law. That's going to be on a separate video. All right, so we're going to go on with our gas laws. We've had Charles, Boyles, and Gay-Lussac, and now we're going to have Avogadro. And Avogadro is a relationship between volume and moles. And so the volume is directly proportional to the amount, the number of moles. So that means the more moles that you have, the more volume that it's going to take up. And since they're directly related, again, we're going to have to divide. So V1 over N1 equals V2 over N2. So here's an example. So I'm going to set mine up. V1 over N1 equals V2 over N2. And I have 0.75 moles, so that's my N. Occupies 1.5 liters. And what volume will 1.2 moles at the same temperature and pressure? So this is going to be V2. So cross multiply and then divide. So I'm going to take 1.5 times 1.2. So 1.5 times 1.2. And then divide by 0.75. And each one of these has two significant figures, so my answer is going to have 2. All right, a lot of times we talk about STP. And STP is an acronym that stands for Standard Temperature and Standard Pressure. So Standard Temperature and Pressure, STP. And standard temperature is at 0 degrees Celsius, which is 273 Kelvin. Standard pressure is 1 atmosphere. So they're just going to slide this into the problem, and you're not going to even think about what this means. But anytime you see STP, you know two pieces of information. You know 0 degrees Celsius and 1 atmosphere. So if it ever says STP, that's giving you two pieces of information. Now, at STP, every gas has the same volume if you have a mole. So 1 mole of every gas has a volume of 22.4 liters. That's called the molar volume because it's the volume of a mole. Like molar mass is the mass of a mole. Now, only at STP is every gas the same. At other temperatures, it's not going to be 22.4. Now, I have then a conversion factor that I can use. 22.4 liters in a mole, or I could have 1 mole as 22.4 liters. All right, so here they want to know what is the volume if I have 2.75 moles. So I start with 2.75 moles. Since I'm at STP, 1 mole is 22.4 liters. So I'm going to take 2.75 times 22.4. I have 3 significant figures, so I get 3 significant figures for my answer. Okay, here's another one. This one says I have 4 grams. Well, if I have 4 grams, I don't know anything unless I get moles, because at STP, it's molar volume. So I'm going to take my 4 grams and use the molar mass, CH4, which is 1 C and 4 H's added up. It's about 16. So 16 grams in 1 mole, and then I know there's always 22.4 liters in 1 mole. So 4 times 1 times 22.4 divided by my 16. I have 3 sig figs, so I'm going to get 3 sig figs in my answer. All right, now a lot of times we're going to see STP and it's going to be involved in a chemical reaction. So if we have a chemical reaction, we're going to need to use those mole to mole factors. All right, so in this case, they say what volume of oxygen is needed to react with 15 grams of aluminum at STP. So I have 15 grams of aluminum. I'm going to use my molar mass to get 2 moles of aluminum. So these are like these 3-step problems that we were doing with gram to grams. So now I can use my conversion factor of my mole to mole ratio to go from moles of aluminum to moles of oxygen, because my ratio is going to be 3 of oxygen to every 4 of aluminum. And then once I have moles of oxygen, I can go to liters of oxygen using that molar volume at STP. So here it is down here, 15 grams of aluminum, divide by the molar mass. Then I'm going to use my mole to mole conversion factor, the 3 of oxygen to every 4 of aluminum. And then I have to use 22.4 liters in a mole. Now, this stuff is not anything new. This was just like when we were going from grams to grams, except instead of using molar mass here at the end, I'm going to use this new 22.4. And once again, I always want to line up and make my units cancel. And since I had 3 significant figures to start with, I ended up with 3 significant figures at the end. Okay, Dalton's law. Dalton says that if you have a mixture of gases, that the total pressure is the sum of all of the partial pressures. So let's say I have 3 gases, 1, 2, and 3. That means if you add up all their individual pressures, that's the total pressure in the flask. So in this case, I have a scuba tank, and I have helium and oxygen. So we have a tank, and we have helium, and we have oxygen. And the scuba tank is 7 atmospheres, and the pressure of the oxygen is 1140 millimeters. I'm going to need that into atmospheres since this one was atmospheres. So 1140 millimeters, and there's 760 millimeters in 1 atmosphere. So 1140 by 760, that gets me 1.5 atmospheres. So 1.5 is the pressure of the oxygen, and I want to know the pressure of the helium. So I'm going to take 7 minus 1.5. That means the pressure of my helium is going to be 5.5. And I'd have, for subtraction, 2 decimal places, 1 decimal place, so I get 1 decimal place is the least amount. So Dalton's law isn't too bad because you just have to add and subtract.